Hello and welcome to the sixth video on hash-based crypto primitives. In this video, we're going to switch our focus to MAC algorithms. So remember that a MAC algorithm is used to enforce the integrity of a message and also the authentication of the sender. It takes as input a message M and then a private or shared key K and outputs an authentication tag. So the sender would send the message and the tag, and then the receiver would be able to recompute the tag using the message and the key, and therefore check that the message was not compromised during the transfer and that the sender was indeed the other person who knew about the key K. So we discussed several approaches in the past, one of them being the idea of encrypting the message with a block cipher in CBC mode and then send the last encrypted block or the so-called CBC residue as the authentication tag. Now, it turns out we have to be careful about this approach, which is called CBC MAC. It has some issues. A more secure approach or implementation of this approach is called CMAC, and there's quite a few others like OMAC and PMAC. Now, you're not responsible to know how these other approaches work. I'm just mentioning them here in case you want to look them up. So that was an approach based on CBC or cipher block chaining. Another approach we discussed was to use either symmetric or asymmetric encryption to encrypt a hash code of the message and use that as a MAC. I'm going to discuss that again here. Actual implementation of this approach include UMAC and VMAC in case you want to look those up on the side. Instead, what we're going to focus on in the rest of this lecture is hashed-based approaches to MAC, and so what we call hashed MAC. The main approach we're going to discuss in the rest of the lecture is called HMAC. But before I do that, let me remind you of one of the previous approaches that we considered earlier. So consider the scenario where Alice is trying to send a message M to Bob. The message is not encrypted at this point, but Bob does care that the message not be tampered with during the transfer and that the sender A be authenticated. So one way to do that is that A and B, Alice and Bob, have a shared knowledge of a key that nobody else knows. And then Alice can hash, so using a MAC algorithm called H in this case, she can hash the message with the key and send that along as an authentication tag to Bob. Okay? Now, one way to do this is to use a regular hash function H and to end up, so a hash function that only takes one input, which is just a message, and to basically build a new message by concatenating the key K with the message M. The double bar here just means concatenation of the bit strings, just like here. So put the key in front of the message and then hash that, get a hash code, and that's what you use as your authentication tag. So instead of using a MAC algorithm, we can just use a regular hash function with a particular input. So the question we want to ask is whether this approach is secure. And the answer is that it's not. So let's describe a scenario in which Trudy, which is the attacker, could do something pretty bad in terms of an active attack. So what does Trudy knows? What does she know? Well, she knows the message M, and she knows the authentication tag. She knows h of k and m. Okay? So let's be a little bit more specific and take a particular scenario. For example, we can assume that h is a block-based hash function, just like SHA-2, which is very common actually. We can also assume that the size of the key is the same as the size of each block. So remember that the message M is going to be broken up into blocks of size, say, 1024 bits. This is just a made-up example, but that's actually a pretty common scenario. Let's assume that the message M that Alice is sending is actually made up of only two blocks, B1 concatenated with B2. Okay? So, well, first let's just look at what happens when we hash this message M. So, what is H of M without the key? Well, this is whatever you get by hashing two blocks, B1 and B2. Now, remember that the way this block-based hashing works is that the hashing algorithm uses a f function inside of it, like the 80 round f function in SHA-2. And so in particular, the way this works is the hashing algorithm is first going to pass the first block B1 through that f function. And let me rewrite this a little bit differently. Remember that there are two inputs to the f function. First, there's going to be an initialization vector for the first block, and then the block itself. So just remember that this is the same as what you get by hashing the first block. And then the chaining, the block chaining in the hashing algorithm is going to run this itself through the f function with the second block as the second argument. Okay? So the bottom line here, and this is nothing new, we're just reviewing what happens when you hash a two-block message using a hash function like SHA-2. You're basically getting whatever you get by passing through f the hash code for the first block, and then as a second argument to f the second block B2. So just keep that in mind. This is just a review of how H, say, SHA-2 works. Now, we can actually describe an attack that Trudy can now perform on this in this scenario. So remember that Trudy knows the message M. So the first thing that Trudy can do is to build a new message M prime, which is whatever M was concatenated with some other document or text X. And this will work for any X, whatever Trudy chooses to add to M. And so if Trudy wanted to replace M with M prime, she would have to compute the authentication code for M prime. And not only that, she would have to compute the authentication code for the key K concatenated with M prime in this approach, which we're trying to prove is not secure. So how would she do that? Well, let's rewrite this argument here as K concatenated with M prime, which is nothing but M and X. Okay? And so now think of this as one message, or just, one message followed by, say, a single block, even though X could be arbitrarily long. But let's make this, a regular message, and let's make this a block. Well, as we discussed right here, the hash code for such a long message would be the same as what you get by running f and applying it to first whatever you get by hashing this first message right here, which is K followed by M, and then as a second input, this block or message X. So that would be how Trudy could compute this hash code for a new message M prime. The problem is Trudy doesn't know everything here, right? Trudy knows M prime because she knows M and she picked X. She knows the algorithm H because that's the SHA-2 algorithm in this case that was chosen. But Trudy doesn't know K. So she should not be able to compute this hash code. However, this is not what happens. So what does Trudy actually know? So Trudy knows what? Well, she knows F because that's the heart, the core of the SHA-2 algorithm, which is a published standard. And Trudy knows X because she picked it. Remember, this is the message she's going to want to add to M. And she also knows this. Why? Because this is the original authentication tag for the message M, which was sent here in the clear. So it turns out that Trudy knows all components of this expression, which is equal to the hash code of M prime. And therefore, Trudy knows or can compute this authentication code for the new message M prime, even though she doesn't know the key K. And yet she was able to compute the hash code of K followed by M prime. So for example, if say M prime was a double zero, simply a double zero, or rather, let's say X was a double zero and M was the message, I, Alice, owe you, Bob, $20. By adding a double zero to the message, she would make Alice say, I owe you $2,000 to Bob. So Trudy could create this message and the authentication code that goes with it, send that to Bob, and Bob would not notice anything at all. It would look like this message is coming from Alice because it was hashed with apparently the key that only Alice and Bob know. So this is a well-known attack on this kind of approaches. So the bottom line is you should not use this approach of inserting the key in front of the message and then hashing that. So how about if you put the key maybe at the end of the message? Well, it turns out there's another attack on this kind of approach that is a little bit harder to implement and it's not as practical, but it's still a problem. So you cannot add the key either at the beginning or at the end. So this is the reason why earlier in the course we described this other approach showed on the next slide where you sandwich the message with the key in the front and in the back. Okay? So I'm not going to say more about this approach, which is actually pretty secure and could be used, but I just wanted to remind you of this earlier discussion of a hash-based approach to doing authentication. But in the rest of this lecture, we're going to focus on another approach, which is very well known and used quite a bit. And that approach is called HMAC.